We continue on the lecture 3 for the Lie groups. Now this lecture is slightly ambitious for speed, but I think we're off schedule already, so hopefully I won't mess it up, but let's see how we do. We may not get the Cartan killing form in this time. Certainly we're going to discuss some representation theory, and if not, I'll carry on at the beginning of my next lecture with the Cartan killing form. Okay, but let's see how it goes. So what we've got so far is the idea of a Lie algebra as a vector space for which a group can act on naturally. And so as I've pointed out, we have a vector space, we have a group action, it's all defined by the adjoint action, group on its own algebra. Why don't we translate that into matrices? Take as a vector space the basis for the Lie algebra. So we use the Lie algebra for like as vectors. And then via the adjoint action, we can read off how the algebra acts on itself to build up a matrix. And then we can work with matrices that describe the algebra. So first let's focus on what we've got. We've got this vector space Rn. So of course we're thinking about what can we do with a vector space. First we're thinking about matrices, rewrite everything with linear transformations. And then second we might be thinking, well, let's also construct an inner product because we can make a lot of mileage with an inner product space. So postpone thoughts of the inner product until later. For now, what I'm saying here is what I've just said in words, that we know how the Lie algebra acts on itself, and this, Jose mentioned the endomorphisms earlier. So G is a vector space with basis vectors, the algebra elements. The endomorphisms of G just stands for the automorphisms of G, which are not necessarily invertible. So it's an action. If they were invertible, the endomorphisms, we could have an inverse and go back, it would be an automorphism. That's all we're just being a little bit cagey. If we're thinking about matrix actions on vector spaces, we're not thinking about GLN, we're just thinking about all the possible matrices when we say endomorphisms. That's the only catch there. So that's okay. And now we can rewrite the adjoint action as a matrix action on the vector space. And there's some notation which is quite important here for the rest of the lecture. So we can write the matrix using a pi, where if the algebra element is x, then we can come up with how the algebra element x acts on the left on the rest of the algebra to read off the elements for this matrix pi. And pi of x will be our representation matrix of x, and it will sit in normally GLN. And we'll call this the adjoint representation. Later on, pi will stand for any representation, and I'll try and make it clear when I'm generalizing. But from most of the beginning, we'll be thinking about the adjoint. So we need some formal definition. So let G be a matrix Lie group. Then a finite dimensional real representation of G is a Lie group homomorphism. So it's a bit stronger than I said. It's not just writing everything down as a matrix. The homomorphism is saying, well, let's keep the properties of the group. So maybe I can write that down. So that, all we're saying by pi being a homomorphism is that, for example, pi distributes over two group elements, which act like this, to give us pi of G1 and pi of G2. So homomorphisms preserve the product structure of a group. That's exactly what we need. We're going to recast group and then algebra elements as matrices, but we'd like to not lose all the important structure of the algebra, so it has to be a homomorphism for that reason. Second, and this is our focus on the algebras, we can define a similar representation on the Lie algebras. Am I louder now? Sorry, I can't tell when it's quiet. Apologies. So if we have little g in Gothic font as a Lie algebra, then a finite dimensional real representation of G is a Lie algebra homomorphism again. And now I'm going to denote the algebra representation with a little pi. So it's that same thing. Big letters for the group, small letters for the algebra. And again, it's going to be a map. It should be from the algebra there, sorry. There. That's correct there. So this is a map from the algebra into matrices, and it's a homomorphism again. Now, the homomorphism on the algebra has to distribute over the algebra action, and we're focusing on the Lie bracket. So if I had two elements in the algebra, and I want to represent them by a matrix, then because pi is a homomorphism, it will distribute over the elements in the bracket. That's the property we're getting for free by stating it's a homomorphism. That might look like something tricky to come up with, but it follows very naturally if you can come up with a representation for the group, which is a homomorphism. Okay? And then by defining the adjoint action of the group, or the inner automorphisms of the group on itself, then you can use that representation of the group via the inner automorphisms of the group to give you back the Lie adjoint action by taking a derivative with respect to the parameter. And you would find then that the homomorphism of big pi comes down to little pi. So we need one more term. So if the representation of the group big pi, or the algebra, its equivalent little pi, are one-to-one homomorphisms, so we don't lose any information, then the representation is called faithful. Okay? So a representation effectively is a way to recast a group or a Lie algebra as a matrix action on a vector space. And because it's a homomorphism, we keep the properties of the group product encoded in the representation. So, some remarks. So we wrote pi as a map from the group for the group representation into general linear group NC. We could have been more general and just talked about general linear transformations on a vector space, like that. Okay. For each representation of G acting on a vector space V, as we mentioned, there's an associated Lie algebra representation, because you could take the group representation with big pi, recast that as e to the little pi, and then read off or try to discover what little pi is. And in blue at the bottom is this comment I was making, that the homomorphism properties pass over from the group to the algebra.
I have a question.
Yeah.
When you write the generators of the Lie algebra as operators, that's actually an infinite dimensional representation, no? A realization of the...
Yeah.
Why you are not including infinite dimensional in this definition?
I suppose I'm trying to take a tour of the subject, and I'm picking out first and foremost simple ideas. But yeah, I've touched on things which are, like you said, that operate out, which acts on the space of smooth functions, infinite dimensional. Yeah, so here I've restricted my interest to finite dimensional, but it's more just so that we can visualize a matrix with n by n, which n is finite.
Okay.
That's all. It wasn't to hide anything. It was just to simplify our attention a little bit. That's all.
Okay. Yes.
Okay. So we need some more terminology. So let pi be a representation of G on the vector space V. Then, if there's a subspace W of V, and under the action of the representation, every vector which lies in W is mapped to something which is still in W, then we call that subspace W invariant. Okay? And a representation with no non-trivial invariant subspaces is called irreducible. By non-trivial, I mean that W cannot equal either the empty sets of 0 or the whole group itself. It has to be some interesting subset of V, okay, rather than all of V or nothing. I think this is probably best illustrated by a small and simple example. So suppose you consider SO2 again, but instead of writing SO2 as 2 by 2 matrices, we write SO2 instead. Trivially, we embed it inside R3. So we write it inside a 3 by 3 matrix, but nothing's going on in the Z direction. So we just put the one entry in. Now, this will act on R3, so it gives us a representation of the rotation group, okay, in R3, but nothing is going on in the Z direction. We're just rotating in the XY plane. So this is a trivial example of something which would be given by, or which is a reducible representation, because the Z, any vector span given as a multiple of the Z basis vector, stays within the Z direction. So the Z axis is invariant in this. Okay? So seeing that, you might think, well, reducible representations, they're a way of sort of encoding a group action in a not very efficient manner. So irreducible representations would be the ones which are most interesting to us, because we're not going to waste any of our representation space, if you like, in encoding the key information about the group. Okay, so we'll be interested in irreducible representations. On the other hand, you may complain at this point that, we've already got matrix Lie groups and algebras. Why are we interested in rewriting matrix groups as matrices? You've got it there in front of you, and that's a valid point. Okay, but so the short answer, I suppose, and it will sound trivial is that it's interesting to know when we can do this. And the longer answer is it will prove useful. And maybe to give you a small comment about it being useful. Well, actually, let me give you a comment that you might make to me that would say, why are we doing this? This isn't very interesting. If we think about SL3, it's written as 3 by 3 matrices, so it's acting naturally on R3. So the basis is 3, dimension space is 3. However, if we were to move over to this adjoint action, the dimension of the algebra of SL3 is 8-dimensional. So if I were to try and write an action of SL3 on its own algebra, the basis space would be 8-dimensional. So I'll have 8 by 8 matrices. And you could cite that to me as a reason not to do this, okay? Which is fine. I think it's important to think through these concepts and what's going on. The interesting point, perhaps, is when we can come up with different dimensions apart from the natural dimension or from the natural representations of representations which are then themselves irreducible. So they're not actually losing any information, but they might actually be easier for us to work with. Okay, so SL3 is not an example. All right. So, but we'll come up with some examples. So we're going to focus first on the adjoint representation. Sometimes, and in Gilmore, it's called the regular representation. So this is given when the vector space itself, as we mentioned, is the Lie algebra. So let X subscript I be elements in the algebra, and we'll consider the adjoint action of some other fixed element Z on each of the elements in the Lie algebra Xi. Okay. Now, it's going to act on Xi to give something else back in the Lie algebra. So that thing must be a sum of the Xi's. So we write that sum on the right-hand side. And using this construction, so we work out the commutators between Z and Xi, we can read off then the elements inside pi of Z, which will be the adjoint representation matrix, the algebra. So we need to work through the commutators, read off the matrix entries, and then we have the adjoint.
Is there a way to relate the PC with the structure constant?
Yeah, exactly. So, these would be the structure constants here. But what I haven't got that's slightly different from the structure constants is a label for Z. Yeah. So if I had Z varying, okay, then I would have another index here on the Z. That would give me another index over here, and that would then run over the whole of the algebra, and that thing would then be the same as the structure constants. Okay. So we should try and compute this for some examples. So consider the adjoint representation of SL2R. So we've got these three matrices, H, E, and F, which span the space of traceless symmetric matrices. Sorry, traceless matrices. Okay? And the commutators for the adjoints are these three, which you can work out by multiplying the matrices together and evaluating and reading on. Now, the adjoint action is going to act on the basis formed by E, F, and H. So it's another example where the natural representation is acting on R2, but the adjoint is going to act on a vector space of dimension 3. Okay. So we write down the matrices for the adjoint as follows. So take H, for example, and consider the commutator of H with any element xi. So first let I equal 1. I've ordered the basis elements H, E, and F as 1, 2, 3 here. And these matrices are written with that in mind. If I change the order, I'd be interchanging rows and columns. So when xi is 1, I have x1 is h. H with h gives me 0. Okay, regardless. So the sum of the elements on the right-hand side is 0. And this first row gives me the terms in the sum of elements on the right. So it's 0, 0, and 0. More interesting is when I is 2. Then I have h with e, which gives me 2e. Okay, so I get 0h plus 2e plus 0f, and then the second row is 0 to 0. Okay, and so on. So you can see that pi of h is diagonal, and you can also go on and work out pi of e and pi of f. And in general, if we take any element in the algebra, so it's a linear sum, so we take a, b, and c to be real, and take the sum of the elements, then we get total representation matrix looks like this. Okay? So these things are useful to write out. I mentioned about SL3. The natural SL3 representation is 3 by 3, and it's a pain here to write out the adjoint representation. Here's just one example. It's an 8 by 8 matrix. Okay? It's good for you to have in mind the size of these matrices and be clear about your vector space they're acting on. It's not so good for you to try and work these things out, I don't think, at this point. Okay? It's good to know it can be done. Similarly, we can also make a adjoint representation for SO3, an algebra we met earlier, by considering the commutators. And now the bases are R1, R2, and R3. Okay. Some comments on complexification before we start doing some things with the adjoint representation. So, let's make a proposition. Let G, little g, be a real Lie algebra, and let G subscript C be something called its complexification. Okay. Then, and what we're doing is we're taking the algebra which was over the reals, so it had real coefficients in the linears, and allowing it to vary to be in C. Okay. Every finite dimensional representation, pi of G, has a unique extension to a complex linear representation, G of C, which is, by the use of notation, also denoted here by pi. I have to tell you we're working over the complex, and it's given as follows. So if I consider x plus iy, that's a complexification of the algebra x and y. Okay? Then we write it out like follows. We take the real part inside of the representation and write pi of x plus, and we make the imaginary part from what was the imaginary thing here. So that's a unique extension. So a comment. If pi is an irreducible representation of the algebra G, where G is over the reals, then it extends to an irreducible representation of a G of C. What are we saying by that? Well, by irreducible, think again about the matrices. We're looking for a way of changing the basis of the matrix to perhaps make one row and one column or more trivial. Okay, so if you can't do that already with pi, all we're changing inside complexification is, well, we're changing it so that the entries become complex. So it's not changing the structure of the algebra, and we're not going to be able to, if pi is already irreducible, then the complexification won't be irreducible. So why do we think about this? It's because complexification results in the unification of some of the more fundamental Lie algebras. So SL2R, SU2, and SL2C, by complexification, end up all being SL2C. So, for example, take, let's see, SL2R. It's spanned by a matrix which is 2 by 2. It's traceless. Okay. And SL2C, we just swap the entries for complex entries. So it's traceless, but now alpha, beta, gamma are complex numbers. But it has to be traceless. Okay. So if you write out SL2C here, you can expand it in terms of real numbers and pull out the imaginary part, and you have one representation of SL2R plus an imaginary number times another representation of SL2R. Okay. So the complexification of SL2R as an algebra gives us SL2C. And similarly, SU2, which is spanned by the Pauli matrices, which I'm writing out in one matrix here. Again, if you take one of these and add to it an imaginary number times another copy of these for different x, y, and z, okay, then we get a larger matrix with complex entries, which now also lies in SL2C. Okay? So, now the basis for SL2C is H, E, and F. The algebra is now complex linear. So part of the reason for saying this was a health warning, I suppose. Because SL2R and SU2 as algebras complexified to SL2C, it's not uncommon for SU2 and SL2 to be used interchangeably with people who aren't making special effort. And I put my hand out, I think sometimes do this. Okay. So our main focus will be on SL2C, but look, we still have the same H, E, and F, and we still have the same fundamental commutator relations. So we're going to think about some representations of SL2C here. And for this example, we're going to return to operator algebras and take the map from a matrix to an operator that we laid out in the earlier lectures, where we take the coordinate vector transpose, we multiply it by the matrix in the algebra and then multiply that on nabla. Okay? So we read off what the three operators are, and inside here we have H, E, and F. Okay? Now, I've labeled each one of these with a little letter M, which will become, the reason for that will become clear in a moment. Okay. And the algebra acts now on the space of smooth functions of Z1 and Z2, where Z1 and Z2 are complex. So consider now the case specifically where the functions are written as sums of terms whose powers add up to n. And that's the meaning of the n. So we have functions of two variables, it's a polynomial, it's linear, and each term has terms whose exponents add to n. So for example, Z1, n minus 1, Z2. Powers of the two add to n. Okay, and we take a whole range. So there are m plus 1 of these types of terms. And each one of these, the powers of Z1 and Z2, will be acting like a basis vector in what will become an m plus 1 dimensional representation. And we won't need to fix m as we go on, but because it's going to be the dimension of the representation, it will be an integer. So the space, which I'm going to call Vm of such functions, is m plus 1 dimensional. And here are, if you like, are the basis vectors. And if you want to coordinate yourself in that space, you specify A0 through to An. Okay. Now we can act with the algebra on this basis. So we take our representation of SL2 as operators in Z1, Z2, and act on a general term in this space. Now H is given as here, so Z1, so we take a derivative of Z1 and then we put Z1 back in, and we subtract Z2 after having taken the derivative of Z2. So the Z1 term subtracts the power of Z1, and the Z1 multiple adds that power back on. All that happens is that the exponent comes down when we take the dZ1 derivative. Something similar for Z2, but we have a minus sign to it. So now the power that comes down is K. The terms stay the same. So, in effect, each one of these terms in this space is acting like an eigenoperator for this operation, I m on H, with eigenvalue m minus 2k. K can vary, so this is true for all. K varies from 0 to n. Okay. The action of pi m of e over here is simple as well. Pi m of e is Z1 dZ2, so it subtracts the power of the Z2 variable by 1 and adds a power to the Z1 variable. So the total sum in the exponent stays the same. We just take 1 from the Z2 and add it to the Z1. So we're staying in the same space, but we now shift. It's no longer an eigenvector. It shifts the power of Z2 down by 1, and we pick up a coefficient. Pi f does the opposite thing. It subtracts the power from Z1 and adds it to the Z2. Okay? We stay in the space because we subtract and add 1 each time and move them over. So these representations as operators act on this space and move basis vectors to other basis vectors. And pi h just reads off and acts as an, well, each one of these terms acts as an eigenoperator. So I've sketched on here. Take this term. Pi m maps this term back to this term but changes the coefficient. Pi of e moves this term down to something in this term, again changing the coefficients. And pi f acts in this direction. So pi e is, let's see, it's lowering the power of Z2, raising the power of Z1, and pi f is lowering the power of Z1. Pi h is leaving the powers of Z1 and Z2 unchanged. Okay. M is playing no role in this apart from being the total sum of the exponents. So pi of e is, you can think of as a raising operator for the power of Z1, pi of x is a lowering operator for the power of Z1. Now, if we took each of these terms as a basis vector, we could go about writing each of these as a matrix which acts on the basis, which is m plus 1 dimensional. And we'd have a representation of SL2, which is acting on this basis. Yeah.
If we do, can we do this kind of mechanism in S32?
Yes, yes.
Then we get the J plus and J minus.
Yes, yeah. So the point about the complexification and the unification, if you like, of my discussion of SU2, SL2R, and SL2C was that you could extract, in principle, the real representation from the complexified representation. So all this works for SL2C, should also work for SL2R and SU2. Yeah. But I didn't write down how you extracted each time. That's the SU2 representation. Yeah, so there's a reason it's also okay. So we could come up with these m+1 by m+1 representation matrices. So comment. So now we have a representation of SL2C, and we have one for every integer m, positive integer, because we just pick the total power of the exponents. So we have an infinite set of representations now. Second, notice that it terminates, because I think we might be wondering, why does it stop here? What happens when pi me acts on the last term? So for example, if you act on the last term, because the representation as an operator of E has a dz2 in it, then it maps straight away to 0. Okay? And similarly for pi mf at the end. So there are vectors in this representation which are annihilated by pi me and pi mf. Each representation on this space is irreducible, so we can show that. Because to show something is irreducible, we need to show there's no non-trivial invariant subspaces. So suppose, contrary, suppose there was an invariant subspace that was non-trivial. Call that subspace W. Let there, since it's non-trivial, let there be one vector in there. So I write out a general vector in the whole space. I'm not presuming the dimension of W is the same as V at this point. All I need is that one of these B coefficients is non-zero. Okay? I don't want them all to be non-zero, otherwise it would actually be a vector in the whole same size space. And I'm looking to find something non-trivial, so it should be less than the size of E. So I need one of them at least to be non-zero, and I don't want them all to be non-zero. Okay? Let K0 be the smallest value for which B K is non-zero. Okay? So that's the smallest value to get. Now act with pi me on that term. Okay. So pi me subtracts one and subtracts 1 from the exponent of z2 and adds it to z1. Okay. So k0 gets lowered to k0 minus 1. Okay. So if this action on the space acts to lower the lowest valued vector, if the coefficient z2 is k0, to k0 minus 1. So it moves us outside of W. So we hold tight to our principle, W must be invariant. So then we say, well, in that case, W has to also include all the lower powers as well. A similar argument for pi of f will make an argument that says, well, it has to also include all the higher powers too. Okay? Because it's meant to be invariant, mapping W to itself, under all the actions of pi of h, pi of e, and pi of f. And in order for that to happen, because pi of v and pi of f are raising and lowering, moving the basis vectors amongst each other, we need to include the whole span. So that means that W has to be V itself, so it is trivial. So this is a comment then that this representation is irreducible because we couldn't find an invariant subspace. So each representation is labeled by one number m, or equivalently, you could label it by m+1, which is the dimension of the vector space. Pi of E and pi of F raise and lower the power of Z1 in each basis term. And there are unique lowest and highest powers of Z1, which are annihilated by the operators. So pi of E and pi of F are raising and lowering operators, if you like. Okay. So these features will generalize when we look at large algebras. We'll look at representations for large algebras, and we will actually try and break down the large algebra representation into these SL2C representations, because these ones we have immediately under control. We have an infinite set of representations, each one labeled by a dimension and of the vector space. If with the representation theory under control on SL2C, if we can map from large algebras down to SL2C representations, then we can take our knowledge of SL2C that we developed here and apply that to sub-SL2Cs within large algebras. And these numbers that label the representation will become important later on. Okay, so we didn't talk about SU2 over Z2 being isomorphic to SO3. There was a couple of slides early on at the end of the last lecture where we looked at an isomorphism between the Lie algebras of SU2 and SO3 and saw how we could try and use that isomorphism to try and build an isomorphism, or at least a homomorphism between the two groups, SU2 and SO3. Okay. So we're going to take this as a fact here. Now, because SL2C representations by the complexification are related to SU2 representations, then we can relate our knowledge of SL2C to SU2, and our knowledge of SU2 via its isomorphic representations of SO3. So there will exist corresponding SO3 representations, one for every dimension. But these SO3 representations are normally labeled by m over 2, where the dimension of the SL2 representation is m plus 1. This m over 2 is called the spin, normally often denoted by j. So notice j can be half integer, and this half comes through because of the representation theory thing we didn't discuss relating these two groups. Okay.
I'm sorry.
Yeah.
Can I ask something?
Yeah.
How do you prove that these are all the finite dimensional representation of SL2C?
Yeah, I haven't proven that they're all of them yet. Later on, we may well make the argument. But the argument that one would make would be to say that the arbitrary representations can be put into an isomorphism with these representations. But I don't know if we'll make the argument at this stage, and we haven't made it yet. But yeah, we haven't done all. All we've got so far is an infinite set, each one labeled by an integer. Okay. Okay. All right. And we can now relate into the physics language spin representations, which correspond to these underlying m plus 1 dimensional SO2 representations. And we just write down a chart converting m over 2 to m plus 1 here, which isn't particularly exciting. But the names of these representations are perhaps interesting. So on the right, we've got the dimension of the SL2 representation. So if it's only one dimensional, then there's only one vector in it. So that's a trivial representation, nothing interesting about it here. If it's two-dimensional, then that's our standard representation where we write SL2C as 2 by 2 matrices acting on some vector. That's a two-dimensional. Okay. That's called the standard or fundamental representation. And the one that we wrote down for the adjoint was three-dimensional. Now, I'm claiming, although I haven't shown, that we can put each one of these operator representations of SL2C into correspondence with the adjoint representation. M plus 1 is 3. Fundamental with the dimension, if the dimension of B is 2, and so on. And we might come back to it later. Okay. A comment about J. Because J is representing SO3 and M is integer, J can be half integer as well. So when J is half integer, it refers to, it's a half integer spin, referring to fermions, and when J is integer, it's referring to bosons. We're not going to say much more than that, I'm afraid, at this point. Given some representations, what can we do with them? Well, we could add them together to make new ones, or we could take general products or tensor products of representations. So in this section, I just want to set out what the direct sum of representations is and also the tensor product. So let's take two representations, pi1 and pi2. It doesn't matter that I'm talking about the group here rather than the algebra. The terminology is the same for the algebra. Okay, so the direct sum is written with a plus and a circle. And we take the matrix representation pi1 and we put it in the top left-hand corner of a matrix. And we can take pi2, the second representation, put it in the bottom right-hand corner, leaving zeros. So this is a square array of zeros here, rather than just a single zero there. So if pi1 was n-dimensional and pi2 was m-dimensional, this total matrix would be n plus m by n plus m. Okay. And from there, we can show that this is a homomorphism as well. Okay. So it's another representation. If Vn has basis vectors E1 to En and V2, has basis vectors F1 to Fn, then the dimension of the direct sum is just n plus m. because the basis in the new space is n plus m dimensional. So the direct sum gives block diagonal representations. And as the representation matrices are block diagonal, they have invariant subspaces. Okay. For example, if we take pi1 and pi2, and we just don't put any vectors in v2, then it acts to transform v1 over to v1. So it maps v1 to v1. So v1 is an invariant subspace. Similarly, v2 is an invariant subspace if we don't put anything in the v1 part of the vector. Okay. So there are two invariant subspaces here. So this is not an irreducible. It's got invariant subspaces. It's a reducible representation because it's not irreducible. The second way of forming a new representation from two that we have at hand is called the tensor product. And it's written in this rather general way. And I've got a cross with a circle between the two representations. And it maps the group over to the endomorphisms on general linear here. So on V1 producted with V2. So if V1 has basis vectors EI and V2 has basis vectors Fi, then the basis of the product is going to be E1 times EI times Fi. So as so if E is varying from say 1 to n, and F is varying from 1 to m, then these new basis vectors are varying from 1 to n times m. So this is an n times m dimensional representation, whereas the direct sum is n plus m. Okay. We haven't specified any properties on this tensor product at this point. It might not seem particularly useful. And here's the comment about the basis and counting the basis. So you might wonder, why are we doing this? So consider the endomorphisms from a vector space to itself. And so let A be one of these endomorphisms in the direct sum. Yeah. Oh, sorry, I've written direct sum. So in general, this is a matrix which is n plus m by n plus m. And so we can split it up into blocks, parts which are n by n, parts which are m by m, and then two parts which are n by m and m by m down here. So the general matrix here is n squared, so it has n and m squared elements inside it to describe it. Whereas if we just focus on the endomorphisms which map V1 on V1 and the endomorphisms on V2, because in the direct sum these two are 0, then this is n squared and this is m squared numbers. So we find that from the direct sum we only get n squared plus m squared bits of information, whereas we'd like to get n plus m squared. So the direct sum representations cannot generate all the endomorphisms of this joined vector space. On the other hand, the tensor product does the job, because the endomorphisms, as we said, of this space when we take the tensor is n squared m squared, and this is the same as the dimension of endomorphism v1 squared times the endomorphisms of v2. Okay. So the direct sum never gives irreducible representations. There's always trivial subspaces, v1 or v2 as labeled here. But it's less straightforward for the tensor product to discover whether or not pi1 tensor bit pi2 is irreducible. So that's the question we'll be interested in. And frequently one is interested in decomposing tensor products into direct sums of irreducible representations. So for example, if I allow me to write product of v1 times v2 tensor space here, then supposing I can split it up into a set of representations on u1, u2, and u up to un here, so I have n of them. I might write it like this. So the matrices which act on this space, which are in v1, v2, must then be, by some change of basis, be able to be written in this block diagonal form, where these blocks here are irreducible parts. This first block acting on u1, and the second part acting on u2, and so on. Okay? So if I can do this, it means there is a change of basis that allows all the matrices and representation to be put into this block diagonal form, which is an interesting thing. When we can do this for all the elements in the algebra, we call the algebra semi-simple. And we'll say more on that at some point soon. So as I'm saying, it requires a change of basis. And it's not generally possible to do this, but one of the most important cases where you can do it is for representations which are important in theoretical physics. So if we take representations of SO3 labeled by spin, and if we take tensor products of them, we can always rewrite them as a sum of irreducible representations of smaller dimension. And doing this decomposition is called the Clebsch-Gordon decomposition. So we were labeling the representation of SO3 by J, where J was actually m over 2. M was this integer value which was labeling the dimension. M plus 1 was the dimension of the SL2 representations we constructed earlier. The Clebsch-Gordon decomposition, just to state it, says that you take J1, so I'm labeling this as the J1 representation of SO3 and multiplying it by J2, then it splits up in this very nice form, which you see often in quantum mechanics, with the highest being J1 plus J2, and you go all the way down until you get to the modulus of the difference. So these are all positive values. And you can always translate these back into the SL2 representations by m over 2 being the spin and m plus 1 being the dimension of the SL2 representation, and write down what the dimensions of each of these things are. Okay. So that's a case when it's possible. Let me make some comments which move towards the classification of the Lie algebras. So having got a description of the Lie algebra as a matrix representation, there are a number of questions from linear algebra which we may immediately ask about the matrices. So perhaps the first one that you'll think of will be, what are the eigenvalues of this representation? Because given the eigenvalues, we then try to diagonalize the matrix. We're going to postpone that discussion for a bit. It will come up in the next lecture. It's a very important idea. But other than doing that, you might make a change of basis and to try and bring all the matrices in the representation to standard forms. So we've got a set of standard forms, and I just want to flash them up and make some comments about each one. So suppose you could find a change, and imagine we're thinking about the adjoint representation, which we know is well defined for every group. Okay. So we might try to obtain the matrices of any adjoint representation in one of these 6 forms as it happens. If we could make a change of basis so that the adjoint was just a matrix of zeros, well then that means that the algebra itself is abelian, because all the coefficients on the right are 0. So if you can do this, it means your algebra is an abelian algebra. The second case, perhaps, if you could make a change of basis so that all the entries are in the strictly upper triangle part of the matrix. So there's zeros on the diagonal and zeros in the lower triangle here. Now, these matrices, when you multiply them together, every time you multiply one of them on another one, projects out one of these rows of off diagonals until eventually, for a high enough power, there will be some power where the matrix becomes the matrix of zeros. Okay. Just, for example, think of a 2 by 2 case. 0, 1, 0, 0 multiplied by itself gives you zeros everywhere. So that's nilpotent. So if you can do that, then there exists some integer n such that pi of x to the n is 0, gives a 0 matrix. Now that means that if we write down the adjoint representation in terms of the commutator on the left, z with xi, and if pi of z for a particular operator is nilpotent, then that means that this matrix has non-zero entries only for j greater than I. Okay. So that means that this commutator, which could lie in this, across the whole span of the vector space, the whole of the algebra, is now being reduced, because it can only now lie in all the values from I plus 1 to n, because all the entries of this matrix are 0 when j is equal or less than I. So it starts to act in a way that collapses down the vector space it's acting on. A slight generalization of the nilpotent matrix is where you've also got some non-zero entries on the diagonal. In such an algebra, if you could write all the representation matrices for the adjoint in this form for an algebra, it would be called solvable. And it's a similar comment to what we just made about how the vector space is being reduced by the action of this matrix because of its form. Okay. Now, this matrix, which is represented, can have a non-zero entry when j equals I. So that just means that there's one extra possible vector here. So by acting z on xi, we reduce the span of the output from the whole of the vector space to a subset, slightly larger than the nilpotent case, but again, the space is being reduced. Okay. And you can come up with a set of invariant subalgebras, each of which is labeled by vi. Let I denote the lowest number of the generator in some lowest number generator in some order that we set up before. Okay. And so you can show that if you start in that part of the space and act, it always either keeps you in that space or reduces it. So these are each invariant. So again, this means that every solvable algebra, or every sort of solvable matrix, upper triangle matrix with entries on it, if you could write that down, it's going to indicate that the matrix has invariant subspaces, okay? And actually has a set of nested invariant subspaces. More classical approaches to the algebras really focus on this structure of the ideals and nested ideals. We haven't focused on it in this presentation. As a subclass, every nilpotent algebra is solved. Okay. The fourth form we might reduce to is this sort of large block, if you like, hook form, where there's just a square of zeros. That's the best we can do in changing our basis of the algebra, is get a square set or rectangle of zeros down here. Now this would mean that the representation is reducible, because take a matrix of this block form, acting on V1 and V2. Okay. Now take a vector which just has a part in V1, it maps over to some new vector only in V1 because V2 is 0. Okay. So it means it has an invariant subspace again, so it's reducible. Gilmore calls these types of algebras non-semisimple. 5. This class that we started to think about just now, where we could take a representation and rewrite it as a direct sum. So these comments apply. All of the matrices in the adjoint representation could be put into such a form by change of basis. In which case we could rewrite the representation as a direct sum of representations. Such algebras are called semisimple. So we're just really focusing on this block diagonal form that could be achieved by changing basis on the matrix. In that case, notice that if we take a simple example where there's just two blocks, A and B, which are non-zero, then of course the representation in A acts on V1 and the representation in B acts on V2, and acts to take V1 into V1 and B acts to take V2 into V2. So you could then start to study each of those independently, which is exactly akin to the statement we made before about the Clebsch-Gordon decomposition, taking a large semi-simple algebra, rewriting it as a direct sum, and studying each of those independently. They don't interact in this representation in any way. So everything you want to learn about the total representations can be learned in these smaller, irreducible representations. Finally, 6, suppose nothing good happens. We can't get all zeros anywhere. Okay, we can't get a block. Okay, then every part of the vector space is being transformed into every other part of the vector space by everything in the algebra. Then such a representation is irreducible. There's no invariant subalgebras. Such algebras are called simple. So it means that every single generator, xk in the subalgebra, can be written as a commutator of xi and xj for some other algebra elements, xi and xj. Okay. So a simple Lie algebra reproduces itself under the adjoint action. It doesn't have the feature that we saw for nilpotent solvable algebras, that the vector spaces act on by repeated adjoint actions are getting smaller, or getting more and more reduced. It's these last two cases that will be our focus. Okay, there's been a lot of killing so far today. Time for a bit more. So, the killing form, I think, is first written down by Cartan. And
can you talk closer?
oh, sorry, yeah, carried away. So the killing form, as it's normally called, I'm calling it the Cartan killing form. I think that's quite popular too. I think it was first written down by Cartan. Okay, so it got misnamed perhaps, and the person responsible is another giant of Lie algebras, Armand Borel. He wrote in his notes Greece not so long ago, the turn of the century. So he doesn't remember why he called it the killing form at any point. So he has no idea why killing's name was associated with it, but he's responsible, he admits he did it. Okay. So the Cartan killing form will be this goal of putting an inner product onto the vector space and finally algebra. It will be an inner product that's invariant under the adjoint action. So we can endow the space spanned by the algebra with an inner product. Now, the space is spanned by matrices. So we might say, well, what's a good, and the matrices may have complex entries in them. And so we might come up with a good, well-behaved inner product. There's already the Hilbert-Schmidt inner product, which is the trace of the complex conjugate of one matrix times the second matrix. And so it's the inner product A with B. However, we're going to get a lot more mileage of doing something which perhaps is not sensible at first sight. So we'll make a very similar definition, but instead of taking the complex conjugate transpose, we will just take the adjoint action again and put it in. So here's our definition of the Cartan killing form. It's defined on elements in the algebra, so let the elements in the algebra as usual be denoted x subscript I and x subscript j. And the Cartan killing form is the trace of the matrix representing the adjoint action for x1 multiplied by the adjoint action for x2. Multiply those two matrices together and now sum the diagonal. Now the output, unlike the Hilbert-Schmidt inner product, will not necessarily be positive definite. It could be 0 and it can be negative. The payoff for choosing to go down this route is there's some interesting meaning to the cases where the inner product is positive, the part of the space where x is 0 and the part where it's negative, which we'll comment on in a minute. We should practice a little with getting clear the idea. So I wrote down very quickly a representation for the adjoint, any element in the adjoint of SL2. Yeah. Okay, so it gave this matrix. So if I want to compute the inner product via the Cartan killing form of this general element AHBE plus CF with itself, okay, so this is what I want to compute in the inner product. I have two copies of the same element in the algebra. Then the instruction is multiply these two matrices together, do it correctly, then take the trace. And so now we get some of them, so you don't have to work out any of the off diagonals, just the trace from form. And we find that we get 8a squared minus 4bc. So this means that if we had taken the element just where a is non-zero, but b and c are 0, then we get something positive. If we took bc being non-zero, but a is 0, we get something negative. Okay. So this split of which elements in the Lie algebra have a Cartan killing form with themselves, which are negative, 0, or positive, has interesting connections, which I'm going to state. So I've denoted the space of vectors in Lie algebra which have negative inner product with themselves, v minus. And the x with x being 0 would be 0, and those which span x with x being positive, v plus. So we have a splitting under this inner product of the elements in the adjoint in the algebra. Okay. So the connection is this. So elements which are in V minus actually correspond to things which are called compact operator generators. When we exponentiate them, a compact generator is something which gives a matrix all of whose entries will be bounded as we vary it. So it doesn't, at some point, some entry doesn't go off to infinity or down to minus. Okay. Think of a rotation, if you like, on the circle. All the things which are in the positive part corresponds to things which are non-compact when you exponentiate them. Now this is the opposite case. Something goes off to infinity in the matrix. A canonical example might be the translations on the hyperbola, which is actually elements of SO11, okay, because there are points which go off to infinity. V0 corresponds to nilpotent elements, which is interesting for us, because we know something about how the nilpotent element acts on each other. They gradually, as they act on each other, reduce. And you can see that they are nilpotent because consider pi of x being a nilpotent representation. And that means that for I greater than j, the matrix has zeros. sorry, it's the other way around. For j greater than I, sorry, that's wrong. The matrix is 0 then. Now, writing out the trace and plugging in the matrix multiplication in this space, and then applying the rules for nilpotent matrices, you see that first the sum reduces because some of the elements in the first matrix are 0 because it's nilpotent. And then second, the ones that remain on the second matrix, they are all 0 because they have only in them the sum of terms which go past, or they are effectively in the form of a transpose of something which is nilpotent, so they go to 0 too. Okay. Perhaps it's best to think of an example and try it out. Take a canonical example is in SL2R, take the representation matrix for E, which is just 0, 1, 0, and 0, and plug that into Cartan killing to show that it gives a 0. It's nilpotent. Again, one can think of some representations that we know a little bit about to convince ourselves that these statements, we haven't proved that we're just making statements here, are sensible. Take again, within SL2R, we can take the difference of E and F and get the basis element 0, 1, minus 1, 0. Now, if you exponentiate that matrix, compute it, you get exactly the rotation matrix. Okay, but now with the minus sign down here. And similarly, take E plus F, which is 1 and 1 on the off diagonals, exponentiate that, and you get an element which is in SO11. We don't know that yet. You can check that it parameterizes points on the hyperbola. So these are the two matrices we get. Because this is a compact rotation, this is a non-compact hyperbolic rotation. Now, the claim was that if we take E minus F with E minus F inside the Cartan killing form and work out the trace of the matrix itself for the adjoint representation, I plugged in the adjoint representations of each of them. Take the trace, we get something which is positive, which confirms the claim. And again, you can do the computation for E plus F and sort of start to begin to convince yourself about these statements.
It's written in the opposite way in the previous slide.
Oh, what is the
V minus, you put there that consists of compacts, operators, but it's non-compact.
Yeah, it's just, sorry, this computation is fine. It's the statement over there, the wrong way around. Sorry, that's bad. Thank you very much. Oh dear. This is the trouble with just making a statement and not trying to prove it. You make terrible mistakes. Okay. Okay, sorry. Thank you. But that computation is fine. Okay, so let me try and round off now and just make some statements. We can use the Cartan killing form in the algebras to, for example, identify the maximal nilpotent subalgebras. So you could split by working out which generators have a Cartan killing form with themselves, which gives 0, and call that space V0, and then split off the compact and non-compact generators. Now, as a process, if you take away that V0 and consider the reduced algebra, call it G prime without the V0 in it. Try again. See, now you've got a small algebra, so you have a different adjoint representation to write out. Again, do the test twice at most. Okay. And if you have any nilpotent operators left, we can show that those correspond to abelian elements in the original algebra. So call the new nilpotent elements that come out from using the Cartan killing form V0 prime. So we have a V0, V0 prime, and we still have V plus prime and V minus prime at the end of all this. This gives a canonical splitting for the algebra, where V0, the first part that came out was a nilpotent matrix. V0 prime is actually abelian, and V0 plus is non-compact, V minus is, I think it's still put the wrong way around. V minus is non-compact, and V prime plus compact. Okay. The first two cases, the abelian and nilpotent, give the maximum solvable invariant subalgebra because the abelian parts of the matrix is written with non-zero entries on the diagonals, and the nilpotent ones are for triangles, so that equals solvable. If we only have the other parts left, then we've got something which is purely semi-simple. And in principle, we could start with any algebra and work out which bits we have, and then start to classify them. So the most general class is non-semi-simple. The most interesting case for us with the representation theory was under control is the same thing. Okay. But we can use the Cartan killing form to try and split up an algebra and then start to classify structure. And I think I should stop at that point. There's my summary, anyhow. Okay. Sorry for running short of time.
Let's thank him. Please. I have a couple of changes. We're going to have like a 30-minute break for so they can prepare this thing for the inauguration, which is going to be at 4:30 as planned. And then from 5 to 6, we're going to have the introductory lecture IV3. Okay? Thanks.
Could you say that louder? Because we can't hear you. Maybe you can want to use the microphone.
Okay. So we have some changes. And we're going to have a 30-minute break right now. And we're going to come back at 4:30 for the inauguration. And then we have from 5 to 6 the introductory lecture IV3.
El cable eso, no vayamos a
Ahorita lo voy a quitar todo esto. ¿Te quitas el...? Mira. No es que sí te molesta.
que no lo vayamos a pasar ahí.
Ah,
Así que va a poner una ronda. La que está mal empacada fue la de ella. Fue agua, no evitaron hacer agua. Ahora se lo va a